Hello and welcome to the RibMorph webcast. My name is George Athanasakis, and today we're going to teach you about the RibMorph software, a GMorph assessment application that allows end users to navigate through the natural channel design process with ease and precision. RibMorph is an assessment and design application that provides the tools right at your fingertips to analyze geomorphic data and develop natural channel design. Today, RibMorph is used widely throughout the world by a number of federal, state, and local governmental agencies, as well as private consulting firms. For more information on RibMorph, please visit us online at www.ribmorph.com or call 866-748-6673. The purpose of today's webcast is specifically to go over geomorphic assessment tools and provide a general overview of the software. So with that, I'd like to go ahead and get started. First off, the way you initially bring up RibMorph is just tap on the icon and obviously the software will open. And then once you open the software, you can either create a new file, open an existing file, or save as and create a new file as well. We also have features that allow you to import and export databases, extract data as well. And so with RibMorph, you can have one database or you can have multiple databases depending on how you want to organize your data. And then with the import and export routine, you can then pull your data together at a later date. So the way that the software works is you will, on the left here is what we call our river tree view. And this is a view into the database. So this is all your geomorphic data sets are basically going to be illustrated in the river tree view. Once you tap on a geomorphic data set, for instance, a cross-section, then the data is going to display in the main window to the right. And then in addition to these main viewing windows, we have these pop-up tools, for instance, regime equations, which basically then allows you to look at, go through and do regime equations, check out the equations while you're working in the main window. So that's basically how the software tends to be organized just from a database perspective. So with that, I'm going to go ahead and just dig into cross-sections and spend some time talking about how you would enter in geomorphic cross-sections. So anytime you're in the river tree view and you want to create a geomorphic data set, what you need to do is do a right-click, and then that will allow you to add a cross-section, profile, etc. So if you choose to add a cross-section, excuse me, you would just then type in the name, hit OK, and that would set up the database. Since I already have a cross-section set up, I'm going to just go ahead and close out of that for now. Okay, so this first cross-section here is a riffle. So if I'm doing differential leveling, I'll just enter in the data similar to the way that I would typically process differential leveling data. Later on, I'm going to show you, if you're using total station or survey grade GPS, how you can pull that data directly in. But in this case, this is differential leveling data. So I'm going to put in tape, foresight. I'm already going to have a benchmark and a backsite entered in, and elevations will be calculated. On the right here are some key notes, some key geomorphic parameters which you may be using in the course of collecting this data. So these key geomorphic parameters are all listed in this drop-down menu. One of the key ones is bankful, BKF. And so if you want RibMorph to read what the bankful indicators are and then come up with bankful calculations, it's important that you identify BKF in the notes. Anyway, the way you could do that is through just a right click and then selecting that parameter. You'll notice across the top we have, cut, copy, and paste, insert rows, delete rows, clear, and then it's pretty important that you identify the facet type. So, we can have a riffle, pool, run, glide, step, or other. And by default, RibMorph always assumes that you're talking about a riffle cross-section. So it's really important that you make sure that you designate what that cross-section represents, because later on when we develop dimensionless ratios and we get into classification, we need to know if we're dealing with riffle cross-sections, pool cross-sections, run cross-sections, etc. Okay, and then we also have a tool over here, HECRAS in or out. And so RibMorph does not compute water surface profiles. It's a geomorphic based software product. So we link with HEC-RAS, and you can either export out RiverMorph geometry files into HEC-RAS, or you can bring in HEC-RAS geometry files into RiverMorph, and you would do that using the HEC-in, HEC-out. Okay, so this is basically how you would get the data into the software. So once the data is in, you can then look at bankful parameters on the graph. And I'm going to start out by just adjusting this graph a little bit. So I'm going to go to Graph Options, and anytime you want to adjust a graph in RiverMorph, there will be this Options icon. Normally it will be just sitting somewhere on the graph. This particular cross-section, there's so many things that you can do with the cross-section that it's kind of in this drop-down menu. But nevertheless, the way that we would manipulate the graph is relatively the same in each one. So in this case, I'm going to adjust the axis a little bit. I'm going to go with the user-defined axis, and I'm going to have it go from 102 to 110. And then I'll probably just put 4 tick marks in here. Okay, so that just kind of shifted the graph down out of the legend a little bit. So you can see that I've got a bankful width of 20, bankful depth of a little over 1, and an area about 21.2. With RiverMorph, the goal is to be very graphical. So let's say you get back in the office and you're just curious about maybe what this particular feature, what the bankful parameters are for that. So you can just drag your mouse down and it'll automatically calculate the bankful features on the fly. And then once you reset bankful, it'll go back to those original bankful calculations. Now, you may want to just show bankful only. If you have an inner berm and you want to show that inner berm, then you would just hit Show Inner Berm on that. And then in addition, if you want to show the width of the flood-prone area, you can then show that on the graph as well. And again, the graph is basically manipulated using these tools under this graph button, and there's quite a ways to manipulate the graph and ultimately show what you want to show with the graph. Now, just one other item on graph option that I'll go ahead and display real quickly. So let's say you have a graph in here and you want to export it out for a report. The way you would do that is under the System tab, you would select the Export File format, and then JPEG, for instance, and then you would hit Browse, and then just go ahead and name it. I'll say XS Riffle, and then hit Save, and then RiverMorph would automatically create that file for you, and then you can bring that into a report, or you can bring it into a PowerPoint presentation. So anyway, that's under the System tab under Graph Options. Okay, so now there's a number of tools on this graph that allow you to analyze the data. So let's just talk about those for a second. So this first tool, Limits, what this does is if you have a hydraulically disconnected area, and what I mean by that is that the water flows through a side channel, and that side channel just doesn't fill up with backwater. And the way that you know if you've got a hydraulically connected side channel is if you walk into that side channel below bankful elevation, you walk all the way through that side channel and go back into the main channel, and you never step above bankful, then that is a side channel that's hydraulically connected. And this would also be known as like a, if it's not hydraulically connected, this would be similar to an ineffective flow area in HEC-RAS. So if it's hydraulically connected, we want our bankful calculations to go through that. If it's not hydraulically connected and it just fills up with backwater, we want to ignore those bankful calculations. So the way that I could do this is I could just enter in X1 and X2 stations to confine the calculation, and I can readily know where I need to, what I need to use for the X coordinate by just hovering my mouse and then reading the coordinates at the bottom on each side. And so this particular cross section, I don't have any side channels below bankful, so it's not, it's not relevant. But if I did, that's how I would do that, especially if I'm in a braided system that has some hydraulically connected channels and others that are not. I'm just going to cancel out of that for now. Okay. So cells, what cells does is it allows you to break the cross section into 5 user-defined cells, And by default, RiverMorph will break it up evenly distributed, but you can make these cells whatever width you want to make them. They don't have to be continuous across the entire cross-section. And then what this does is it allows you to analyze either hydraulic properties about the entire cross-section, or you can specifically look at one particular cell. And where this becomes important is if you're dealing with sediment transport and you're dealing with a braided system with multiple channels, most of the sediment transport tends to occur in the deepest channel. So this would be a way that you would be able to break up the cross-section into cells and then look at these different cells and how sediment transport may work through those cells. Okay. Depression is another way to take out an ineffective flow area, but it only allows you to take one out. So my suggestion is just always use the limits tool for that. What overlay does is it allows you to then overlay cross sections, which you typically do if you're monitoring. And in this particular database is not set up as a monitoring database, so I don't really have an overlay to do. But the way it would ultimately work is you just select the cross section. All the cross sections in your database are listed in this drop-down menu. You would select the one you want to overlay, hit OK, and then you could then overlay them, as well as then determine the difference in the area from one year to the other. So you can get a feel for how that area has changed over a period of time. Okay, so that's basically how the tools work here. And then drawing is just a tool that allows you to do a sketch out a cross section with by just doing mouse clicks. So if you were doing a design and you wanted to just check out a cross section and see what the properties of that particular cross section are, then you would use this tool and then export that sketch out. Okay, so that's basically how the graph works. Now you'll notice here on the summary tab, this is when we start to get a lot more detailed information about that cross section. So what's the bank flow elevation, what's the flood prone width, entrenchment ratio, what's the depth ratio, the wetted perimeter, etc. And one thing I want to point out here too is that the entrenchment ratio here, which is shown right here, is 9.85, but that's because I entered in a width of flood prone area. So I did a WFPA override. If I didn't do that, the entrenchment ratio would be 1.47. So I want to point some out here on the graph. Okay, you notice this width of flood prone area. Well, the data does not go high enough to really designate what that width of flood prone area is. And like most softwares, when we run out of data points, RiverMorph just assumes vertical. So in this case, the width of the flood prone area is about 1.47, or I'm sorry, the entrenchment ratio is about 1.47, but the width of the flood prone area is actually about 30, okay? But in this case, when I look at the graph, I can obviously tell that the data points just didn't go out far enough. So if I didn't take my data points out far enough to define that width of flood prone area, where I can still get the correct entrenchment ratios, I can just do an override and then type in what I know that width of that flood prone area is, which in this case would be about 200. So anyway, this would be the overall channel information, and I can also look at left and right halves of the channel, which by default RiverMorph splits it in half. But if I use this mouse function tool and set it to split station, I can define where I want to split that station up. So if this was a deep pool, for instance, I may want to do it at the deepest part of the pool. Okay, so that's how I would then be able to look at the data. And I'm going to go ahead and reset bank flow here real quick, as well as showing a berm. Okay. So that's the summary tab, and I can see now that at this point I don't have enough information to really classify this stream, but I can tell based on a broad level classification that the entrenchment ratio of 9.8, almost 10, with depth ratio of 19.3, I'm headed towards a C classification. Hydraulics by stages. This is up to this point we have been mainly just looking at the bankful properties of that river. What hydraulics by stages allows us to do is to then look at hydraulics by different stage increments. And what I'm displaying right now is really a what we refer to as hydraulic geometry. And so I can create a graph of any of these parameters. So for instance, let's say that I wanted to look at how area varies with depth. So I can then create a graph. So this is a hydraulic geometry plot of how area varies with depth through that cross-section. So you probably have heard hydraulic geometry talked about a lot, and that is basically what is being displayed now on stages. But if I want to get more detailed information, let's say that I want to determine velocity discharge, I can select a velocity discharge equation. In this case, I'll choose Manning's. And then there's plenty of ways that I can get a Manning's in there. In this case, I'll just say base it off of Lomarinos, which requires the D84 input parameter. There's several sediment transport equations that we can do, which require some input parameters. And then there's an energy slope, which I can either use the constant slope, or I could define a depth-slope relationship. So for instance, we always do hydraulics at a riffle. So at low flow, our riffles are steep. So I can define a depth for low flow and what that slope is. And then I can also define at bankful, riffles flatten out. So I can then define a slope at bankful, and then what that depth is, and then what that slope is. And then typically above bankful, slope is relatively constant, and then I can vary slope with depth in between low flow and bankful. Or I can just go through and do a constant slope, whichever seems most appropriate. So then I hit finished, and now I've got a lot more calculations in here. And if I go to graph, you can see that I have a lot more options that I can graph. So now, for instance, I may want to look at how shear stress varies with depth. So now I can create those shear stress graphs with depth. So that's what hydraulics by stages does. It basically allows you to go through and do a more in-depth analysis. And if I had been using cells, I could look at multiple cells for this. And then with Rivermorph, we want to allow you the opportunity to store all the data with your database. So for instance, if I have a photograph, I can then store that photograph. Although I'll point out that what you're storing is the path to the photograph, not actually the photograph. And that's by design, just to keep the database such that it's not overly large. Okay, so that's basically cross-sections in a nutshell. And just want to go through some other geomorphic parameters here relatively quickly, but I probably won't spend as much time as what I did with cross-sections. So profile, again, like cross-sections, the way you create a profile is you do right-click and add a profile. And then this is differential leveling data, so I'm putting in the distance, CH, water surface, bankful, and up to 4 user-defined points, which I can also rename those points. So if one was low bank, high bank, I could rename those, etc. And then with Rivermorph, if I'm entering in actual elevation data, I would just select this elevation data. And then if it's rod readings, I can enter in either a water surface rod reading, or if I'm recording water as depth by measuring up the rod, then I would press water as depth. But in this particular case, these water surface are rod readings. Okay, and then I can designate the location of where my cross-sections are occurring on the profile by just entering the station here. And then I'll note here too that if we're doing riffle, if I want to see where the feature is, I can type in riffle or R, run or U, pool or P, or G or glide. And Rivermorph needs to see that as the first thing in the notes. So for instance, if let's say I want to call that top of riffle, if I want to then see that feature on the graph, translate it over on the graph where that riffle was, the way I'd want to type it in would be riffle space top. Because if the first thing is riffle or an R, then Rivermorph is going to know to then designate that on the graph accordingly. Okay, turning points. This is where, again, putting in benchmark information. If I have to do a turning point to complete the profile data, then I would put that in here. And the key here is that you have to designate the station at which that turning point kicks in. So in this case, I'm on the benchmark all the way up to 141, I should say. Then my turning point is at 145. So beginning at 151, now I'm on the new height of instrument established through that turning point. Okay. Now, ultimately, what we want to do is get measurements. So the way that we do that is we create a graph of that cross section, and then we can using your mouse, make a series of measurements. So, for instance, I'm just going to illustrate this. I'm going to make some pool depth measurements. So I'm going to drag up with my mouse up to bankful from the deepest part of the pool up, and I'm going to capture those measurements. So then what I would do is just minimize this, and then I've made a series of depth measurements. So I would go to Dmax pool and then hit copy and paste, which this data is very close to what I already have in there, but I'm just going to leave what I have in there. But the way I would do that is then click on this, and then it would load those values up. And then after I make that measure, I reset list. I go ahead and pull the graph back up, and now I make another measurement, like, for instance, pool-to-pool spacing. And then, again, I would minimize that, and then I could copy and paste that in. So with RiverMorph, so there's a number of measurements that you need to make. And we have a measure guide here that then shows you where those measurements need to be taken. So, when we do a pool depth, we measure up to bankful. From the center of the pool, the run, we do about the center of the feature. Same things with a riffle. But in the case of a glide, we tend to do it right at the tail out of the glide or the top of the riffle. And then we measure pool slopes across the pool, and we would measure pool lengths from the end of the run, start of the pool, to the end of the glide. So anyway, there's pretty